This is part of the BocaPhysics series on electromagnetism. In today's lecture, you'll see how the Maxwell stress tensor is defined and how it can be used to solve problems. First, let's consider two like-charged particles moving with velocities v1 and v2 respectively. Velocity vectors are blue. We'll consider a snapshot in time. From this point of view, v1 moves upwards and v2 moves to the right. The two charged particles exert equal and opposite electric forces on each other. These force vectors are purple. A magnetic field will also be generated due to the motion of each particle. Magnetic field vectors are green. The magnetic field, however, is not given by the Biot-Savart law. Notice the field due to charge 2 points out of the screen at the position of charged particle 1, and a magnetic field due to charged particle 1 points into the screen at the position of charged particle 2. As a consequence of the particle's motion and the magnetic fields, there will be a magnetic force. These forces are depicted by yellow vectors. Notice that the magnetic force on the first particle points to the right, but the magnetic force on the second particle points straight up. We've arrived at a shocking truth. Newton's third law does not hold in electrodynamics, and this has profound implications as far as momentum is concerned. In today's lecture, I'm going to derive the Maxwell stress tensor, and I'll apply it to the example of a uniformly charged sphere with a certain surface charge density sigma and with angular speed omega. And we'll calculate the force of attraction between the northern and southern hemispheres using the Maxwell stress tensor. Now, the big important point that I made in those simulations I just showed you is that Newton's third law does not hold in electrodynamics. It holds in electrostatics and it holds in magnetostatics, but not electrodynamics. Now, that probably comes as a shock because way back when you were taking general physics, you derived conservation of momentum using Newton's third law. Well, if Newton's third law no longer holds, where does that leave us? Conservation of momentum is a fundamental law of physics, and it must hold in electrodynamics. The answer is that the fields themselves carry momentum. Now, this leads to some very subtle arguments regarding the nature of momentum. And in fact, something like 55 or 60 years ago, Shockley and a co-worker, and I believe the co-worker's name was James, published a paper where they proposed the concept of hidden momentum. And anyway, that term is very controversial. It's controversial even to this day. People are still writing papers arguing over the meaning of hidden momentum or whether it should be discarded altogether. Basically, it arises from, or generally speaking, it's momentum that is in a surprising place. I guess maybe that's the best way of phrasing it for now. Anyway, a shortly forthcoming lecture, I'll discuss what hidden momentum means in greater detail. But for today, we'll just look at the Maxwell stress tensor. I'm going to begin here with the Lorentz force law. So suppose we've got a charge distribution. So therefore, the force acting on that distribution of charge is equal to the charge density times the electric field plus the current density crossed into the magnetic field, and we're integrating over the whole volume. So if this represents a force, then therefore this, lowercase f, is the force per unit volume. So that's charge density times the electric field plus current density crossed into the magnetic field. I'm going to make use of some vector identities and also some product rules and, of course, Maxwell's equations to come up with the definition for the Maxwell stress tensor. So just as a reminder, Gauss's law tells us that the divergence of the electric field is equal to the charge density over epsilon naught, or permittivity of free space. And our second equation is that the magnetic field is divergence free. That reflects the physical fact that the magnetic field had, or rather that there have never been observed any magnetic monopoles, and not for lack of trying either. Okay, we also have Faraday's law. And of course, it's the curl of the electric field is equal to minus the partial derivative of the magnetic field with respect to time. And notice I am putting that term over the right-hand side. That's really for calculational convenience, and if you really want to be picky, to a fault, I think, you just want to have the true source terms on the right-hand side and all the fields over the left. Anyway, Ampere and Maxwell's law, curl of the magnetic field is equal to U naught times J plus U naught times the displacement current. So the displacement current is epsilon naught times the partial derivative of the electric field with respect to time. I'm going to make some substitutions here. First of all, I'm going to replace rho using Gauss's law. And I'll replace the current density using the Ampere-Maxwell relation. I'll read it off. We have epsilon naught times the divergence of the electric field times the electric field plus 1 over mu naught curl of the magnetic field, cross product with that with the magnetic field, minus epsilon naught times the partial derivative of the electric field with respect to time crossed into the magnetic field. I'm going to make use of the fact, it's already here, if we take the partial derivative with respect to time of E cross B, I can write this out. This will be partial derivative of E with respect to time cross B plus E crossing the partial derivative of the magnetic field with respect to time. Okay, so to replace this term with this minus this. First two terms I've just left the same, and this last term is, let's make sure to leave anything off here. I'm going to have an epsilon naught there. This is epsilon minus epsilon naught partial derivative with respect to time of E cross B plus epsilon naught times E cross partial derivative of the magnetic field with respect to time. I can use Maxwell's law to replace this partial derivative of B by minus curl of the electric field, right? So there, let's replace using this expression, Faraday's law, sorry, to replace the partial derivative of B with respect to time. Okay, so I'm going to go ahead and flip the curl of B over to flip the order of this cross product, and pull all the electric field terms up to the front. make this expression symmetric in electric and magnetic fields, I'm going to add an additional term to the magnetic field. I'm going to add a term that has this form. The reason why I can do that, of course, is because the divergence of the magnetic field is equal to 0. So basically, I'm just adding 0 to it, but it's making the expression symmetric. So the first term here will be 1 over mu naught divergence of the magnetic field times the magnetic field minus whenever mu naught be crossed into the curl of the magnetic field, and then we got one final term minus epsilon naught partial derivative with respect to time of E cross B. Okay, so we're making progress here. So E crossed into the curl of the electric field is equal to 1/2 the gradient of the electric field squared minus the electric field dotted into the gradient of the electric field. So I'm going to replace these terms in this expression. Okay, so we've now broken apart, ripped everything apart, and we've got epsilon naught, divergence of the electric field times the electric field, minus electric field dotting gradient times electric field. We have a similar expression for the magnetic field, only we've got 1 over mu naught out in front instead of the permittivity. So this is a divergence of the magnetic field times the magnetic field minus magnetic field dotting the gradient of the magnetic field. And then we've got these terms, minus 1/2 epsilon naught gradient of the electric field squared plus 1 over mu naught gradient of the magnetic field squared. And then we have our time varying term, which is minus epsilon naught partial derivative with respect to time of E cross B. And I'll leave this up here just for a minute. I'm going to have to erase the left-hand side of the board to give myself a little bit more room. Okie dokie. So, let's define the Maxwell stress tensor. To have the form of epsilon naught I and j here represent the Cartesian components x, y, and z. Also recall that the product of delta has value 1 if I is equal to j, and is equal to 0 if not. Okie dokie. So what I can do is then say, well, if I take the divergence of all this lengthy expression, that is going to give me all of these terms here, okay? And if you're feeling ambitious, you can go ahead and work everything out. I'm just going to leave it at this stage. And then we have our final term here, we can't forget about that, is actually equal to epsilon naught mu naught partial derivative with respect to time times pointing vector. So we see the pointing vector making an appearance. Finally, the force on a charge distribution, therefore, is going to be equal to the volume integral of the divergence of the Maxwell stress tensor minus the partial derivative of the pointing vector with respect to time and integrated over that same volume. Now I can make use of the divergence theorem to convert this first integral into a surface integral. So this is equal to Maxwell stress tensor dotted into normal, and we're integrating over the surface that bounds this volume, okay? Now remember, the normal in this case is the normal to the surface. And then again, we still have minus epsilon naught mu naught volume integral of partial derivative of the pointing vector with respect to time. And that is how you calculate force in terms of the Maxwell stress tensor and also the pointing vector. Now, Maxwell stress tensor is a second-rate tensor. So you see down here from this integral, when I take the dot product of the Maxwell stress tensor with the normal, I'm actually going to get another vector back, okay? Be nice to have a kind of a feel for what these terms mean. So basically, you can write the Maxwell stress tensor in matrix form. So we'll have Txx, Txy, Txz, Tyx, Tyy, Tyz, Tzx, Tzy, and Tzz. Okay? And notice that this tensor, actually you can see it from that form over there, is symmetric. So what that means, of course, is that the xz component is equal to the zx and the xy is equal to the yx. And the yz is equal to zy. Now, to kind of, I guess, make this concept a little bit more concrete, you want to go back to a concept that's
familiar. When you go back to thinking about hydrostatic pressure, that's an example of a stress, right? Okay, so what do the diagonal terms here represent? Well, the diagonal terms represent pressures. And the off-diagonal terms represent shears. So again, thinking about hydrostatic pressure, in a fluid, the pressure or the stress rather is normal to the bounding surface, okay? So that means you're not going to have any off-diagonal terms in that case. If you're just talking about a regular old fluid, furthermore, these three terms are actually going to have the same value. So basically that's a reflection of the isotropy of the medium. And so in that case, for fluid, when you're calculating hydrostatic pressure, that's just going to be a scalar quantity, okay? So but anyway, that's going back to something that's a little bit familiar, and we're, of course, have more terms here than that. So this is the most general expression for a stress tensor. Okay. Erase that, let me erase this. And I should also point out that it's always possible to diagonalize these matrices so that you'd only have three terms. And you've got one term, let's say, is in the direction of the electric field. Let's say the electric field is in z direction. And for the sake of the argument right here, we're just going to forget about the magnetic field terms. Okay, so if the electric field is the different one, we're going to basically have over here epsilon naught Ez squared minus 1/2 epsilon naught squared plus EY squared plus EZ squared. And then for these x and y, and you'll have a similar expression for the y component, okay? But by assumption, where the electric field is only pointing in z direction, so therefore your x and y terms drop out. So that means your last term in the expression is going to have the value epsilon naught Ez squared over 2. And these two first ones are going to have the opposite sign. These two terms give you the elements of the stress perpendicular to the electric field, and this final element gives you the stress, gives the element parallel to the electric field. Notice these two carry minus signs and this carries a positive sign. You'll probably get a problem where you have a stress tensor that has this nice simple form. Well, as you might guess, the algebra can get pretty messy with these, and it's very easy to get tripped up on notation. So I think the best way of showing you of how to handle this surface integral is just by means of an example. So let's get to that next. Before we work through that example, let's look at a couple of simulations. I haven't found too many cases in the literature where people have plotted the Maxwell stress tensor. A notable exception is Panofsky and Phillips. However, I think it's an even more interesting diagram appears in a paper by Hermann and Schmidt, which appeared in the American Journal of Physics back in 1985. We have the full reference available on the BocaPhysics website. Anyway, what they did was plot, or rather resolve the stress tensor into vector components, and they plotted some of those components for the case of two infinite line charges that bear a like charge, and then two infinite line charges that bear unlike charge. I thought it was really interesting what they did, so I wrote up some code that reproduces their simulations. So let's take a look at that right now.
Stress tensor can be visualized in the following way. Stress tensor represents the force per unit area acting on a surface. The momentum current density tensor is equal to the negative of the Maxwell stress tensor and represents the flow of momentum. To get a handle on how the momentum current density behaves, let's look at the simplest possible field, that of a uniform electric field pointing to the right. The x momentum current density is represented by a vector of a kind. We can take either the first row or the first column. Remember, the Maxwell stress tensor is symmetric, and hence so is a momentum current density tensor. In this case, the x momentum current density vector points to the left. If the field is reversed, the x momentum current density still points to the left. This behavior can best be understood by considering a parallel plate capacitor. The plates attract each other regardless of whether or not the field is reversed. Let's consider an infinite line charge. Notice that the streamlines do not have cylindrical symmetry. This is because we're considering the x momentum current density. Further, the streamlines form closed circles originating and terminating on the wire. If we consider the y momentum current density instead, this would amount to a rotation of the present simulation. Two unlike charged wires, streamlines that return to the wire, give an indication of internal stress. Essentially, the electric field acts as if it were pulling each wire apart. Streamlines that start on a wire and end on the other wire give an indication of the attraction between the objects. Now let's consider two like charged wires. Once again, the streamlines that begin and end on a single wire give an indication of internal stress. The electric field vanishes at the midpoint between the two line charges, and so no momentum is transferred along the line joining the two line charges. The streamlines in this system that start on one object and end on the other give an indication of repulsion between the two charges. Notice that these streamlines start on the outside of the wires.
Okay, so we want to calculate what is the force of magnetic attraction between the northern and southern hemispheres of a charged spinning shell. This shell spins with angular speed omega, it bears a surface charge density sigma, and its radius large r. We want to calculate the force on the northern hemisphere due to the southern hemisphere using the expression we just derived. The second term is going to be 0 because you're dealing with static fields. So let's, for reference, write down what Tij is equal to. And we have an electric field, or term to the electric field, and we're going to disregard that because we are only interested in this problem, the force of magnetic attraction. So we're just not going to worry about calculating that, we're just going to concern ourselves with this term here. So this is 1 over mu naught Bij minus 1/2 Product delta of ij times b squared. I and j, of course, represent the Cartesian components. In this case, it's useful to represent the Maxwell stress tensor in matrix form. And notice how I've written subscripts here. The reason why I've got txy and txy here rather than txy and tyx is because this matrix is symmetric, so it's perfectly legitimate to do that. Now, this really isn't necessary, but I think it makes it a little bit clearer if you write things out in nauseating detail. So I'm going to write my normal component in terms of its x, y, and z components. Okay? And when I do that, and I take the dot product of this and this, basically I'm going to wind up with another vector. This really looks incredibly messy. However, if you recognize that this there's a symmetry to this problem, therefore the x and y components are not going to contribute. They vanish. And so the only non-vanishing component is going to be the z component. Okay? Those are going to be 0, and if you're feeling ambitious, you can go ahead and work those out. Okay. dA, we're going to be integrating over this hemispherical bowl. Only we're going to take our surface to be just outside of the shell. Okay? And we've got a contribution from the bowl. And we got a contribution from the disk as well. If I look at TXZ, what is that equal to? Well, that's just 1 over mu naught BX BZ. TYZ is just equal to 1 over mu naught BY BZ. And yeah, that's right. And TZZ is equal to whatever mu naught BZ squared minus B squared. 1 over mu naught BZ squared minus b squared over 2. Okay, so if I only look at the z component here, before I actually write down what b is equal to, I'm just going to multiply things out and add them up. So if you notice, in each of these first three terms, you have a factor of bz in common. And if I look at these sums, I've got bx nx plus by ny plus bz nz. Well, that's just equal to b dot n. And then our final term contributes b squared over 2 nz. Okay, so we've gone as far as we can go without writing down what b is equal to. The easiest way I have of remembering what the magnetic field looks like is to think of this as the same way as a uniformly magnetized sphere. Okay? In that case, the magnetic field inside is uniform. It has value 2/3 u naught magnetization times z. However, we are not dealing with a uniformly magnetized sphere, so if I make the substitution that magnetization is replaced by sigma omega r, then I come up with the expression for the magnetic field. It's just, I just find it a little bit easier to remember things this way. The exterior solution is going to be that of a dipole, just a simple magnetic dipole. And if we assume that the magnetization is pointing straight upwards, which of course is what we did right here, that's equal to mu naught m over 4 pi r cubed times 2 cosine theta in the radial direction plus sine theta in the theta direction, and that's the exterior solution. Now, we know that magnetic dipole moment and magnetization are related by this expression. It's just, if I replace the magnetic dipole moment by magnetization times 4 pi over 3 r cubed, and then I need to replace m by sigma omega r. I just substitute in for m 4 pi over 3 sigma omega r to the fourth. And that is equal to u naught sigma omega r to the fourth over 3r cubed times 2 cosine theta in the radial direction plus sine theta in the theta direction. Okay, so I'm going to have to erase some of this to give myself a little bit more room to work. Okay, so in my expression to calculate the dot product of the Maxwell stress tensor and the normal, the only component that I really need to explicitly write out is the z component. Well, that's already right for the interior solution. For the exterior solution, however, and I'm just going to write this down, the z component down, rather than multiplying everything out. Basically, all I'm doing here is replacing the radial unit vector by its expressing Cartesian components, and doing the same thing for theta. And the only thing I'm saving are the z components from that. Otherwise, I'm going to run out of space really fast. So this is equal to 2 cosine squared minus sine squared theta. And I can replace minus sine squared theta by cosine squared theta minus 1. And this becomes 3 cosine squared theta minus 1. Okay, so we're going to first look at the hemispherical bowl. In that case, the surface element is equal to r squared times sine theta d theta d phi. And we'll be using the exterior solution here because our surface is just outside of the hemispherical, or just outside of the hemisphere. Got a factor in common. Okay, because I've got a BZ and a B, both of these quantities have a factor of mu naught sigma omega r to the fourth over r cubed, so I can pull that out. It's going to have a square out front. Now I need to write down what BZ is equal to. That's just 3 cosine squared theta minus 1 times b dot n. In this case, I don't have to do a lot of math here because the normal component is just in the radial direction, so therefore only this term survives. So it's just going to be times 2 cosine theta. Now for the second term, we have minus b squared over 2. So again, you're going to have that factor squared that's already been pulled out front. And that contributes 4 cosine squared plus sine squared theta. And then also we can't forget about nz. Well, the z component, the unit normal vector, is just cosine theta. I mean, basically, it's just the z component of the radial unit vector. Okay, so now I've got everything written down. Not quite there yet because I do want to just have these terms in terms of cosine squared. So if I replace the sine squared by 1 minus cosine squared theta, I will wind up with 3 cosine squared theta plus 1. Okay, so I am making slow but steady progress. And also, I don't want to forget a factor of 2. Don't want to forget about that 3 there. Okay, so I'll pull a factor of 2 out of here. Okay, so we're almost to the solution or the contribution from the bowl. So that's mu naught over 2 sigma omega r over 3 squared 9 cosine cubed theta minus 5 cosine theta. And we're going to integrate from 0 to 2 pi of over the phi direction, and there's nothing in there, so that's just going to be 2 pi. And we're going to integrate from 0 to pi over 2, because it's just over the hemisphere, just the upper part of the charge sphere. So we've got sine theta, and now we've got all this stuff out front. And we wind up with minus mu naught pi over 4 sigma omega r squared over 3 that quantity squared. And now we need to figure out what the contribution is for the disk. So let me just leave that up there for a minute. And I'm going to still have to erase this part here. To calculate the contribution from the disk, we'll take the surface element to be r dr d phi. And in this case, the magnetic field is going to be uniform. Why? Because the disk is inside the sphere, so therefore we'll be using this quantity here. Also, if we look at the normal to the disk is in the z direction, but remember the normal points away from the surface, or out of the surface. So therefore, pointing away from the surface is going to be the minus z direction, and that gives us a minus 1 there. And since the magnitude of b is just bz, after all, b is only pointing in the z direction, we wind up with minus 1 over mu naught b squared over 2. And we're calculating the z component, which is in fact the only non-vanishing contribution. That 2 cancels with that one. One of those 2 cancels with that one. And we've got a minus 2 pi mu naught. If I add this to this, I will get minus pi mu naught over 4 times sigma omega r squared quantity squared in the z direction. And there is your solution. So this was a very long problem. As I said, it's really easy to get tripped up on the algebra once you start getting into tensors.